Right, so today's topic is graphs of polynomial functions. And really I want to now link all these ideas together. The part of it where you can use your graphing calculator to solve, but also the part of it where you have some algebraic skills that you can use to work with things as well. And really those are like two halves of like the same coin. There's the graphing half of the coin, there's the algebra side of the coin, and really they should mean the same things when you're done. So I'm not really doing anything new today, I'm just kind of summarizing. Fair enough? So, I found these pictures somewhere, maybe a textbook, where really any sort of shape, we should be able to find a function that fits it. Like this particular bow in the harp right here, in a way, isn't that kind of like a quadratic, or no, a quartic maybe, if we kind of kept it going, where it starts here, it's going downwards, you go around the edge, this comes back here. Doesn't that kind of have a bit of a shape to it? Like maybe an upside down to the power 4 graph? This one right here, maybe that's like a cubic kind of graph, the way it's kind of working. It depends on whether you actually do another rise in the mountains or not. Does that make sense where I'm going here? So a lot of things are actually graphed when you can find a function that fits it. So here's a quick summary of what we've talked about so far. In terms of patterns, am I in your way by the way? You're in it? Okay. In terms of patterns, you need to know just the even versus the odd. Okay. Even things would be like x to the 2, x to the 4, x to the 6. And really, if I wanted to, I could ask you to do x to like the 18. I wouldn't, because that's dumb. But like, wouldn't a graph of x to the 18 have roughly the same shape to it? Where it's going to start and end on the same side of the graph, and then it's going to have a whole bunch of waves in the middle. Now, how those waves turn out really depends on the function. I could probably write you guys this function though. Let's try it together. This is to the power of 4, I bet, right? Well, this x minus 3 means that there's probably an x plus 3 on it, right? If it goes through x minus 1, it means there's probably an x plus 1 on it, right? Now, over here, see how it doesn't actually go through even numbers? This could be because it ends up being something, I'm just pretending here, I don't actually know for sure, but like maybe it's x squared plus 7x plus 2, and this needs the quadratic formula to get, oh goodness, what's wrong here? To get these two answers. Does that make sense? Two of the things could be factored out and give you nice whole number values, and then the other two are from a quadratic formula. And I'll put some question marks here just because I made up random stuff. I don't know which one it is. You know what I'm saying? Okay. How would the quartic look if the quadratic formula didn't provide you any answers? If there was like a negative under the square root sign, how would that change it? Like it wouldn't go below the axis, right? So it might have looked like here to there, and maybe it does like a little flip like that, but it doesn't actually go below the axis. You know what I'm saying? So, because of the fact that it has a positive leading coefficient, whatever this value is out front here for A, we know it's going to be positive though because of the shape of this graph right here. How could you solve for that leading coefficient? You guys remember from yesterday on the test? If you need to solve a leading coefficient, what else do you need? Any other point on the graph. Okay. The y-intercept, by the way, is often a good choice if you can see the y-intercept. Because then you could plug in, like, say, 0 for x, and then make it equal to y, and plug in, say, 30 for y, something like that. It can help you solve it. See how these two things kind of melt together now? Here's a cubic function. All right, if I were to write this out, this one's probably a little easier to do. Let's see if we can actually write the whole function. Let me just erase all this mess. Okay, so based on this graph right here, it would look to me like we should have an x plus 3, right? Due to the root of minus 3. We should have an x plus 1 due to that root right there. And that one looks like it goes through x minus 2 because it goes through plus 2, right? Now, if I were to throw an a value out here, tell me something about the a value. Not maybe what the number's value is, but is it positive or negative? Negative. Now, I don't know what negative number it is. It could be negative 1, negative 2, negative 3, negative 1.49. Right? It could be any value there. So what we probably would want to do here is, like, say, use the x-intercept right here, or the y-intercept right here, as, like, our other point to try to figure out what that a value is. I feel like it goes through 6, probably. So I would plug in 6 for y, 0 for x. Three times 1 is 3 times minus 2 would give you minus 6. A times minus 6. Let's just write it like this. Minus 6a. So divide both sides by minus 6. Actually, this one was really convenient and easy. It looks like the a value was negative 1. I mean, it could have been a 2 or a 3 or a 4. It just worked out to be 1. But the negative makes sense, though, right? It should have been a negative value because of the fact that we knew that it has that shape to it. Right? When a cubic or a linear or any sort of function goes with like the downhill slope, it should have a negative coefficient. So I won't actually do this, but if you had to write this final equation, it would be negative x plus 3 foiled into x plus 1 foiled into x minus 2. You just foil the crap out of that thing times by negative 1. You guys could do that, though? And so what I'm really doing is I'm merging our two skills. I'm being able to look at a graph, and I'm being able to write an equation. Or I can give you an equation and say, tell me about the graph. Now, I mean, you do have a graphing calculator. So if I start to give you an equation, you can always type it in, but it doesn't hurt to know the basic properties as well, because sometimes they throw weird things in, like they throw in like the letter B, and the letter A. And I showed you a couple of questions like that on the test even yesterday, right, where you can't really use your graphing calculator quite as well. You can try to guess and check, but it's not efficient. So here's kind of some summary slides about just the two different types of polynomials. You've got your odds, which are linear, cubic, quintic, right? Your 1, 3, 5, 7s. The domain of these and the range of these is always everything. The reason for this is the graphs always go cross quadrants, right? It may have like a little flip in the middle. It may just have like a little half turn. It may do a whole bunch of these things, right? But it's always going across the grid, right? So because of that, every x and every y value is possible. Here's another thing. There has to be one root. At least one root. I guarantee it. Why does there have to be a one root for all these things? Why can't there be 0? Because it has to cross the line, right? Like if I drew a grid on this thing here, it has to cross the axis at some point, right? So I guarantee you there is at least one intercept here as a root. Right? There may be 2 or 3 or 4. Like it could do this and have 2. It could do this and have 3. It could do this and have a whole bunch. You know what I'm saying? But there has to be one. I guarantee there's one. And there's also a y-intercept. What's the easiest way to figure out what the y-intercept is if it's in standard form? How do you figure that out just like that? What do you call the velocity? Constant term. Yeah. So, wait, have I talked to you guys about multiplicity before? I think I have, but should I recap it? Do you remember what multiplicity is? Okay, we do a better job here then. Multiplicity would be a graph like this. If I give you x plus 1, x minus 2, x minus 2. This is a cubic. But what's happening in this graph here is you have an intercept here at minus 1, and you have like a multiple intercept over here at 2. And so when you draw this thing, it's going to go like this, and it's just going to barely touch and then come back around again. Because of the fact that you have more than one of these x minus 2s, that's how it just glances. Does that make sense? That's known as a multiple root. So this would be a cubic function with 3 factors. Because look, I factored it 3 times, but only 2 roots. Cubic function, 3 factors, 2 roots. So that's multiplicity. Okay, then here's your even degree polynomials, and these always have like a quadratic-ish shape. I mean, they could look like this. They could look like this. But they always start and end in like the same hemisphere, if that word makes sense. Like it either starts and ends at the top of the graph, or it starts and ends at the bottom of the graph. It doesn't go across quadrants, right? So because of this, the range is always then greater than or less than. And you just have to figure out the highest or lowest of all your vertexes. Because there might be more than one, right? Like here's a turning point, here's a turning point, here's a turning point. You better figure out which one's the lowest, that's all. Here would be the highest one. How many roots does it have to have? Trick question, doesn't have that in it. Because it's entirely possible that I could have given you a quartic that looked like this. See how nothing crossed? So that's actually possible. When you guys try some of the questions that are in like the skills journals, some of them may not actually be factorable. And the reason why they're not factorable is because the graph looks like this. Like nothing factored. Therefore, you could spend forever on it and you'll discover that nothing ever works, which is frustrating. So, make sense? Okay, so here's kind of a slide just talking about all of the terms and skills you hopefully know. Okay, so first of all, do you know the factor and remainder theorems? Do you know how to use those? So, let's start with the remainder theorem. If you want to know what the remainder is, you plug in the opposite value of what you think is a factor. So like if I give you x minus 2, plug in 2. If you just do that, it tells you the remainder. Now the remainder theorem on its own is not all that exciting, but if the remainder is 0, well now you found yourself a factor. So hopefully these two things kind of work together, and that should help you find the roots of a polynomial function. You do need to know how to solve as well. Right? Solving would be like, let's say, if I gave you x plus 2, x minus 2, right? This would have just been factored. Okay? But if I asked you to solve, solving usually means that it's also equal to 0, and then you'd say, well, x then is 2 and negative 2. Does that make sense? So just make sure you know the difference between just find the factors and take it one step further and tell me what x equals as well. Okay? You should know how to use the quadratic formula and regular factoring. I should add to this list, you should also know how to do long division or synthetic division. Right, those are some skills that hopefully you know how to use. And then today what I want to do is I want to remind you that you can do a lot of this stuff sometimes. Not always, because they write really clever questions, but you can also use your graphic calculator. So I want to remind you about how to use the buttons for value, 0, min, max, and intercept, and how that can help too. So, let's do an example. Let's sketch a graph of this, and let's do it first without our graphic calculator, and then later let's do it with the graphic calculator to confirm that we know how this works. So two sides of the same coin, one with algebra, one with calculator. So if I were to graph this thing really roughly, right off the bat, I should know the intercepts, right? Because if this is y equals x minus 1, you should have an intercept at 1. If it's x plus 2, you want one over here at minus 2, and one over here at minus 3. What's the y-intercept going to be? How'd you get that? You're right. How'd you get that? Yeah. I mean, I don't actually want us to FOIL this out, but if you just did a quick imagine in your head, at some point you times the minus 1 by the 2, and then at some point times that by the 3, wouldn't that give you a minus 6? So even then I know where another point is, down here minus 6. So that's that minus 3, 0, minus 2, 0, 1, 0, 0, minus 6. So I'm going to need a calculator to get this thing started. And then for the next part here, all we got to do is just kind of connect the dots. What's the leading coefficient, positive or negative? Well, that just means that it has to start down here and end somewhere up here, that's all. So I'll just use your common sense and connect the dots. So, I mean, it's not going to be square. You have to like curve it a little bit, but this is going to go up to maybe about there, turn around, go down to there, go through there. Yeah, that'll work. That should be its rough shape. Does that make sense? I remember a diploma question one year where to test that kids understood this concept, they gave them something like this. I'm just going to make one up here. They made it like y equals x minus 2, and then like say x plus a squared. And then they asked kids which graph could be the right one. So let me just make some possibilities up here. So here's a. I'll just do a and b. I don't know. which one of these graphs could be the right one, A or B? B, right? I mean, for a lot of different reasons. First of all, this one's quadratic, so I moved that up right off the bat. Because hopefully you'll recognize that this, and the second one makes it cubic, right? But I mean, even if the third distractor might have been C, where it looked like this, how do I figure out between B and C right here? See how this one is x minus 2? X minus 2 means there needs to be a root at 2. Okay, well, let's pretend this is at 2. This one over here could also have been at 2 in theory, right? But see how this guy's squared right here? That's that multiple root. And the 2 one is not the multiple 2 one, right? So that's why it has to be this one right here, where whatever this a value is, I don't know what it is, it's going to have to be that multiple root that hit right here, so that the one for 2 was right there. You know what I'm saying? And it was a really clever question, because you can't type this in your graphing calculator, because you can't use a variable for x and another variable for a. You can't do both, right? You just have to know these properties. Makes sense? Now, that being said, not everything is worth the time to do by hand. Like, for example, this particular one right here is cubic. We could take the time to try to solve it for, you know, some bracketed stuff like this. But there's 2 things I want to point out. One, if it's not necessary, it's not worth our time, you guys have to learn how to be efficient. Okay? Because you only get like 4 minutes a question. So don't be doing stuff unnecessarily. But the second reason is not everything can actually be factored as nice whole numbers. So sometimes it's just better just to go to your calculator if you can. So let's just graph this in the calculator. It's negative 2x to the power 3. Don't graph it just yet if you do have it typed in. Just hold off on pressing it right there. So get it graphed. But just don't press the next button. Because before we do, I just want to talk through some of the concepts. Although I don't know the exact ins and outs of this graph, I do know a couple of things. Tell me something about this graph before you even press the button to do it calculator. Is that? Y-intercept's at negative 4, so I know that. What direction generally is this graph going to go, uphill or downhill? Downhill, right? The negative leading coefficient is going to start it up here and end it down here. Is it going to have an x-intercept? For certain. It has to. It crosses the axis at some point. Does it have to be on a nice even number, though? It might be. It might not be. If it does happen to hit on a nice even number, then it means we probably could have done some factor. We just didn't. There's actually the possibility that it has up to 3 intercepts as well. So okay, now let's graph it. Okay. So as I look at this, it looks like it definitely has an intercept over here. It came back up. It looks like it's just touching right there. But I need to go a little bit closer to take a closer look. You know what I'm saying? Like right there, that could have been a multiple root, but I'm really not certain. So you could like say zoom in. Or something like that, zoom in. And then just put the cursor over in the spot we want to look here. Let's see whether that actually crosses once, twice, or maybe it doesn't even cross. I feel pretty good that actually is crossing at 1. How can I confirm that that is touching right there at 1? What other buttons in the calculator could I do to confirm that? Maximum will work. Maybe a faster one would be to find the value when x is 1 and just see whether it actually is right there at 0. You're not wrong, Brooke, though. You could have done a maximum. Okay, so 1 and some dumb number that's basically 0. So, I mean, with this information here, I should know what the graph sort of looks like. Now, let's say that we actually did want to factor it. I know we didn't bother at first, we just went to a graphing calculator. Tell me something about the equation in factored form. What would it look like? If there were, like, say, 3 brackets, tell me what 2 of those brackets are going to be. Say louder, Marco. Yeah, there's going to be 2 of them that have to be an x minus 1. Does that make sense? Right. The reason there have to be 2 of them is because this is like one of those double multiple roots that's sitting right there. I can probably guess what the other one's going to be, by the way, without doing longer synthetic division. I need there to be a 2 as the very, very first one here. And this is provided in x, and this is provided in x. So I'm going to want a minus 2 to start. Right? Because when I FOIL out the first terms, x times minus 2x is the only way I'll get to minus 2x over 3, right? And then if I look at my last term, I need the last one to be a minus 4. Well, this one's minus 1, and that's minus 1. That brings you to positive 1. If I want the last one to be minus 4, it better be minus 4. So it looks like I actually need x minus 1, maybe minus 2x minus 4. Oh my goodness, it's still looking very nice enough. Did that logic make sense? How I managed to just guess and check the very, very last factor? Minus 2x minus 4. Because that's the only way it'll work, right? For your first term, minus 2x, you'll need x times x. You need one more x, so there's an x here. But you'll need a minus 2 to make that first one work like that, right? And then for the 4 at the end, 1 times 1, well, then you need a 4, and you'll need to be negative. Does this look like it has a negative leading coefficient? Well, I mean, it does if you know what you're looking for. There's kind of a negative sitting right here. But here's a better way of writing the equation. Someone else might have written it as minus 2, x minus 1, x minus 1, x plus 2. What did I do? Yeah, just out of just purely this guy right here, I pulled the minus 2 out. I threw it way at the front, the very, very beginning of this whole thing, right? If you pull the minus 2x out of this guy, it's out here now. And then that's x, and then minus 2 times plus 2 is the minus 4. So there, I kind of did a hybrid on that one, didn't I? Rather than doing long division or synthetic division, which is a pain in the butt, right? I kind of used my own logical intuition. I used my graphing calculator a little bit. Like, I didn't rely entirely on it. I used some common sense, and I was able to reverse engineer myself an equation. You know what I'm saying here? Two sides, same coin. You can do it all algebraically. You can also use your graphing calculator to kind of do it partially, both. All right, let's try this one. So before I even type it in, let's just talk a bit about what I'm expecting here. I've got a negative x to the 3 graph, so it should have some sort of downhill slope. What's its y-intercept though? Well, way the heck up here at 12 is going to be a y-intercept. There could be 1, 2, or 3 intercepts. I don't know how many, but I'm expecting a couple. Or I'm expecting 1 at least. So let's try graphing it. Let's go negative x to the 3. It's not right. Negative x to the power of 3 plus 13x plus 12. Oh, I better check my Windows sets back here. Okay, so as I look at this guy, it appears that there's 3 roots, because I kind of expected there could be 3. So, down to here, up to there, back down. I know I'm not exactly the scale here, but that's the rough idea. Some of you guys are working away here. How can you calculate the x-intercepts? What are some methods you could use to try to find where these intercepts are? Probably the fastest way is to go to the table. The fastest way is to go to the table, because you might just be able to pick them out lickety split. Like, as I look through them here, it looks like there's one at -1. And it looks like there's one over here at -3. And there's one over here at 4. Let's say that they weren't nice whole numbers, though. You could have gone second, calculate the 0. Remember how to do 0? And you go like on the left-hand side and on the right-hand side to try to find where they are. Something like this. Okay, but this should be enough to get me going, right? So now if I want to write the rest of the equation in a factored format, wouldn't it be x plus 3, x plus 1 x minus 4. Wouldn't that be its factored version? I didn't even need to use synthetic division. I managed to figure out all of just using a calculator. But this isn't correct. We're actually not done yet. What did I miss? Leading coefficient. Yeah, if you're going to do something like this, this isn't a problem, but you have to make sure you finish. We know there's a negative causing it to have that sort of directionality to it. So I better figure out what my leading coefficient happens to be. Now, you can try what we've done before. You pick a point off the graph. I'm going to look at the y-intercept. So the y-intercept needs to be 12. Isn't 3 times 1 times minus 4, isn't that going to give you a number of 12? Only it's going to give you minus 12. So I don't actually have to put a different number in front. I don't need to put like a 1 or a 2 or a 3. I need a 1 in front, but it's going to be minus 1. So my final answer could be minus 1, x plus 3, x plus 1, x minus 4. That seems to make everything fit, right? 3 times 1 is 3, times minus 4 is minus 12. With the negative 1 in front, it becomes plus 12. There's your constant term. X times x times x is x to the 3, but the minus makes it minus. So, does that make sense? So, my goal here, again, if I'm not making it clear here, I want you guys to be able to apply both your graphing calculator skills and your algebra skills, because it may be faster to try to do some of your synthetic long division stuff or factoring just by using a calculator. Right? This may be more efficient. There's more than one way of doing it. Okay, the last thing I'm going to show you a couple of word problems. You're going to get one. And sometimes it's going to be a dumb, stupid, silly context like this one here, where I found this one somewhere. You're making a big Rice Krispie square. I don't know why, but it's like 1 by 2 by 5 feet. Yeah. And what you're going to do is you're going to remove the same amount from each dimension. So you know how it's going to be like a prism? You're going to take the same amount off of each dimension. What we're going to try to do is make an equation that we can solve from this. And it may just be best if I just show you how this one's done. It's a dumb context, okay? I know the scenario is silly, but the principles behind how we're going to apply this, you're going to have to do some sort of word problem at some point. So it's normally 1 by 2 by 5, right? That's normally what it is. And that would be like your volume. Makes sense? But if I want to try to throw some more information in here, it actually says that it wants the volume to eventually be 6. So I'm going to change out the volume and make the volume become 6. So far, so good? Now, normally what would the volume be? 1 by 2 by 5, wouldn't that be 10? So we somehow have to get it down to 6. Well, the way you're going to do that is on the side that has the 1, you're going to remove an unknown amount. And on the side that has a 2, you're going to remove that exact same amount. And on the side that is a 5, you're going to remove an unknown amount. It's this step right here that most kids get confused at, because if you get a word problem, you're going to be asked to write yourself your own equation, and then probably solve your own equation. Do you guys see how I managed to pull this out there? It used to be 1 by 2 by 5, but each of the dimensions is now a little bit less, so I subtracted the x from each of them, and we want it to equal 6. So here's 2 options. We could boil the crap out of this thing, subtract 6 to the other side, and then try long division. That's that. Or we have a calculator. Try this. Try 1 minus x. Try 2 minus x. Try 5 minus x. And then see what that equals 6. And do 2 lines. If I do 2 lines, where I figure out where one of them is kind of the volume here, and I want to figure out where it equals 6, I'm going to get some sort of funky looking cubic, and there's where it equals 6. What calculator tool should I use now? What's the button combination use? Intersect, yeah. Now, I gotta point one thing out here. It sure looks like it intersects twice. So I'm gonna try to calculate the first one here. I've got an x value of about 0.2679. And it may intersect over there a little bit later. I'm going to try to intersect over there. Does it intersect? Sure looks close. Oh yeah, it does. I've got like a 3.73 maybe. I don't know which one's the right answer. Negative. Yeah, Jessica's got the idea here. Is everybody okay with how I found those numbers before I move on? You guys able to get the like 0.26 and the 0.2? On this one over here? Did you get the 0.267 number? So yes or no? No. Let me come check the pressure. Oh, okay. What Jessica? You know, maybe it crosses in there twice actually. Maybe that's why. I bet you it crosses in there twice actually. Okay. Well, either way, the point I want to make is still the same. This answer and this answer are going to be wrong. Why? Jessica, can you say it again?
Because if you use the big number, you'll end up at the table.
Yeah. Remember how your Rice Krispie was a 1 by 2 by 5, and you're trying to hack a little bit off, and you're subtracting x from each one here? Did they take 1 and subtract 4 in the real world or something like this? That doesn't make sense, right? Did you take 1 and subtract 3.73? You couldn't. I mean, you have a Rice Krispie square that is defined by 1. I can't go backward. You can't have negative Rice Krispie square. You know what I mean? So this would be a good scenario here where we actually pull off a couple of extraneous solutions here. Right? Remember, extraneous solutions are ones that when you check them back in the original sort of scenario, they're really not logical. That's what we kind of have here. Even though we solved them, it's not reasonable that somehow you have 3 and 4. This is a good example. Even though the scenario is completely ridiculous, do you guys kind of see how the scenario kind of worked? Where first of all, you have to write yourself an equation and make up your own polynomial, you know, kind of from scratch, and then you have to do some work with your polynomial to try to solve for like an x value. So, there's an example of you having to make up your own equation. The other possibility is they might actually give you an equation along with a word problem here. So I think this is our last one, right? Okay, so let's do this one, then we can take a bit of a break. Here's the scenario. A medical research team has determined the amount of reaction time for a exposure to some sort of drug is based on an equation here. So, I mean, there's not a lot of context here, but it seems to tell you that you have a certain amount of time that it takes for you to react to a drug. So, I don't know. Some drugs, I guess, react in 5 minutes. Some that take an hour. So let's graph this thing. First, it gives you a little bit of a hint. It says, let's use a domain of -5 to 5 for t. That's graph this guy here. I actually used the wrong word here. T is my y variable. When you talk about t as y, should I call it a domain? What word should I use? Range, yeah. Okay. So let's use the y from -5 to 5. Now, I didn't actually tell you what to use for the other variable here, from x. But I feel like -10 is not really a logical idea, because if d is the amount of drug absorbed into the blood, would negative make sense? No. So maybe let's go from 0 to 10. We'll start there. Let's see what this looks like. Okay. So I've got a little bit of a cubic here. It's actually a little out of range here. So. Okay, so let's find the x and y intercepts here. To find the y-intercept, oh, hang on, I'm still using the old graph. That's dumb. How about I type in the new graph? -3x cubed plus 3x squared. There, okay. Did you guys get that one now? Yeah. Alright. So even as it was right here, You know how we went from 0 to 10 over here? I don't think we need to go from 0 to 10, because this thing just kind of flopped down right away here. So let's maybe go from 0 to 3, maybe. D is the amount of drug being used. 3 milliliters might be plenty in this particular example. So. Okay. What's the y and x intercepts over here? I don't actually care what the values are. We can do that later. But what do they mean in the context of the function? If this is a graph right here, essentially looking like this, plotting the amount of time, and this one right here is plotting the amount of drugs in your system. Let's just kind of talk this through here. What does this point right here mean? What was that? Not quite. Because right here, this would be where you have like a certain amount of drugs in your system, and time is at 0. Since this is drugs, like, well, what is that number right there? Is that at 1? I'm pretty sure it's at 1 on your side. It's at 1. So what that means is that you have 1 milliliter of drugs when the time is 0. That makes sense? That's what this x-intercept means, right? It means that D is 1 when T is 0, so you have 1 milliliter when you started. It's kind of backwards, eh? Because normally you put T on the x-axis and D on the y-axis. What does this intercept over here mean? Well, this is 0 and 0, right? So this would mean that your dose would be nothing and time would be nothing. So I want to reread this one here again. It says the reaction time to exposure of a drug is this. So I don't think this is actually how long it's been. This is how long it takes for you to react, let's say. So if you have no drugs in your system, how long does it take for you to react? It takes you no time to react, because there's no drugs in your system. Does that make sense? Whereas if you have 1 milliliter of drugs in your system, apparently that also happens instantly as well. Does that make sense? Your reaction time is still instant. Whereas like this point right here, why don't we find this maximum point here? What that would mean right here, why don't we calculate it fast? Maximum value. Um, 0.666 and 0.44. What does that mean, that point there then? Well, 0.66 would be you have a dose of 0.66 milliliters. If your dose is 0.66 milliliters, it's going to take your body 0.44 minutes for you to actually react to that drug. I think what it's saying here is that if you give someone the right dosage, it happens right away. If you give them too little of a dosage, it takes your body a while to actually recognize the drug and actually work with it. Does that make sense? So if you give them nothing, it doesn't take any time for them to react because they're already done, right? If you give them 1 milliliter, they also reacted. But if you give them, like, say, 0.66 milliliters, then it takes them half a minute to catch up. Does that make sense? So that's actually part C. We just solved that. What dosage would have the longest reaction time? Didn't we just calculate that right here? Wouldn't this have the highest reaction time possible? So if you were looking to try to maximize your dosage and you want to have the longest delay before the dosage actually occurs, you would use 0.66 milliliters. Okay, the one thing I didn't talk about here is the restrictions on that domain of the graph. Where should we actually cut this off? You know how like I let the window go from 0 to 3? Where would be a more logical spot to cut it off at, actually? 1. y at 1, what happens after 1? So it's going down here into the negatives. Now, what's on the y-axis? Your amount of reaction time. Should you have a negative reaction time to a drug being in your body? That doesn't make sense, right? I can't put a drug in my body and then it reacts negative 3 seconds later. So I would say the logical restriction to the domain of the graph is that x has to be within 0 and 1. That would be a logical restriction. These last two examples are the ones that drive kids crazy because you're going to get a word problem. It might be in the quadratic polynomial section, it might be in exponential and logarithms, but somewhere along the way they're going to give you some sort of word problem where you have to like use a graph or make yourself an equation and kind of interpret from it. And I struggle with this one as a teacher because the scenarios are so varied. Like the first one I gave you was a Rice Krispie square, which is such a dumb idea. This one here, hopefully the idea makes sense, but like, doesn't it seem backwards that time is on the different axis rather than drug? Because really what they're doing is they're inserting an amount of drugs into your body, and then they're seeing, well, how long does it take for you to react? And normally we put time on the other axis. So they could give you something like this where you really have to like think your way through it. So, well, anyways, that's my lesson. So I guess two main things. You need to know how to apply this sort of stuff to like a word problem scenario. And then secondly, that whole coin analogy of, can you use a graphing calculator to factor? Can you use algebra to factor? Can you use algebra to kind of get a picture of what it looks like as a graph without needing a calculator? Can you kind of do all of these things interchangeably, depending on what skill would be necessary? So, that's all I got. You guys have any questions? Okay. Maybe take a quick break if you want, because I talked for quite a while. And then for the last little bit, I guess if you want, keep working on that assignment. It's not due until after the break, but you probably want to get it most of the way done so you don't have to do it over your reading week break or spring break or whatever you call it.